A strange pattern is spreading across the planet, like 5 different doors shaking in one house. Colombia, Indonesia, Japan, Spain, and the United States are all reporting earthquakes, and the map seems to be blinking faster. But if these quakes are connected, what could possibly reach across oceans, continents, and thousands of miles of rock? And if they are not connected, why does the world suddenly feel as if the ground itself is trying to get our attention? If you come here for real science, clear answers, and mysteries without made-up doom, subscribe now and stay close to the evidence. Earthquakes do not begin with the ground moving. They begin deep below our feet, where huge pieces of Earth's outer shell slowly push, pull, and slide against one another. These pieces are called tectonic plates, and they move so slowly that you cannot feel them moving on an ordinary day. A plate may travel only a few centimeters in a year. That is about as fast as your fingernails grow. But the plate is as wide as a continent and far heavier than any machine humans have built. When its edges lock together, motion does not stop. Stress keeps building inside the rock. Then, at some weak point, the rock breaks or slips. The stored energy races outward as waves, and those waves make the ground shake. That sudden release is an earthquake. This is the basic story behind every quake on Earth, but the details are never exactly the same. A shallow quake can shake a city hard, even when it is not the largest event ever recorded. A deep quake may be much stronger, yet its motion can spread in a different way and be felt across a wider area. Magnitude tells us how much energy an earthquake releases at its source. It is not a simple volume scale where a number 5 is only a little bigger than a number 4. A rise of one whole magnitude means roughly 32 times more released energy. That is why a magnitude 7 is not just 2 points larger than a magnitude 5. It releases about 1,000 times more energy. In everyday language, the numbers climb slowly, but the earthquake power climbs quickly. For a long time, people knew only about the earthquakes they could feel. A small quake in a remote desert could happen and vanish from history without leaving a written record. Today, thousands of sensitive instruments listen to the planet every hour. These instruments are called seismometers. They can detect tiny vibrations from a quake that no person notices, and computer systems can compare signals from stations around the world. A quake that would once have been invisible can now appear on a public map within minutes. That fact is important, because the modern earthquake map is not simply a picture of what Earth is doing. It is also a picture of what humans are able to detect, report, and share. And that is where the mystery begins. A recent list can seem frightening because several real events appear close together in time. The list may include a major earthquake in western Colombia, a sequence around Indonesia, a powerful event in Japan, smaller shocks in Spain, and felt earthquakes in the United States. The locations look scattered, but the planet is full of active faults. Colombia sits near one of the most complicated meeting points on Earth. The Nazca Plate moves beneath the South American Plate along the Pacific side of the country, while other faults cut through the Andes. A plate moving under another plate is called subduction, and it can produce very large earthquakes. On August 10, 2026, the United States Geological Survey reported a magnitude 7.4 earthquake near San Jose del Palmar in western Colombia. Its estimated depth was about 10 kilometers, which is shallow enough for strong shaking near the surface. The event was felt across a wide part of the region, and the number of people exposed to strong shaking was estimated in the millions. Before that event, a person looking at the map might expect the Andes to remain quiet, because there had been no headline in the last few hours. That expectation is understandable, but it is wrong. A fault does not become dangerous only when a camera is pointed at it. What scientists actually found was a large release of stress in a region that has always been tectonically active. The quake was serious, but it was not evidence that Colombia had somehow switched on a planet-wide chain reaction. It showed that the same slow forces that shape the Andes are still operating beneath the surface. The next detail changes how we read the map. A large earthquake is often followed by smaller earthquakes called aftershocks. They happen because the main rupture changes the pressure around nearby faults, leaving the surrounding crust to adjust. Aftershocks can continue for days, weeks, months, or sometimes longer. They do not mean that the whole planet is shaking in sympathy with one location. They usually belong to the local family of movement created by the original quake. So if a map shows many dots after a major event, the dots may look like a new outbreak. In reality, many are echoes of one large rupture. They matter greatly to people living there, but they do not prove that distant faults have been awakened. Have you ever looked at a map of earthquakes and assumed that many dots must mean one global event? If so, leave that thought in the comments and tap like if you want more explanations that separate real danger from scary patterns. Now move west across the Pacific, and the story becomes even more active. Indonesia is spread across a long zone where several plates meet, including the Indo-Australian, Eurasian, and Pacific systems. Its islands sit along the famous Ring of Fire, a broad belt of earthquakes, and volcanoes around much of the Pacific Ocean. The name sounds dramatic, but it describes a real shape on a map. It is not a single crack circling Earth, and it is not a ring that suddenly lights up all at once. It is a chain of plate boundaries, trenches, islands, and faults where the moving crust often produces earthquakes. In Indonesia, the ocean floor can slide beneath island arcs. Water trapped in the sinking rock can help melt material deep below, feeding volcanoes, while the locked plate boundary stores stress for earthquakes. This means one country can experience many different kinds of seismic activity in different places. The first expectation is simple. If Indonesia records a strong quake, people may expect the next one to be in the same area. Sometimes that happens because aftershocks follow the first rupture, but Indonesia is so large and so geologically complex that separate sequences can also appear in different islands. Recent BMKG, Indonesia's Weather and Geophysics Agency, reports have shown small and moderate events around areas such as Flores and Sulawesi. Some events are only a few kilometers deep, while others begin much deeper below the seabed or islands. Depth changes how the shaking travels and whether an ocean quake could create a tsunami. The important discovery is not that Indonesia has earthquakes. Scientists have expected that for centuries. The important point is that several active zones can produce earthquakes during the same period without being physically joined into one giant fault. A quake in Flores does not need to pull a hidden lever beneath Sumatra. A quake in Sulawesi does not automatically push Japan closer to a disaster. The distances are enormous and the fault systems are separate, even though the deeper plate motions belong to the same broad engine. That engine is heat inside Earth. Our planet is not a cold, solid ball, all the way through. Deep heat slowly moves material in the mantle, the thick layer beneath the crust, and that movement helps drive the plates over very long periods. Here's the part that often gets missed. The word simultaneous can mean two events happen within hours or days, but geology often works across thousands or millions of years. Two unrelated earthquakes can line up on a newsfeed, even though in Earth's deeper timeline they are ordinary separate events. Indonesia also reminds us why magnitude alone is not enough. An offshore earthquake can raise tsunami concern if it lifts or drops the sea floor. A land earthquake can damage roads and buildings without creating a wave across the ocean. Emergency agencies check the location, depth, fault movement, and sea level data before issuing warnings. That process can feel slow when people are frightened, but it is designed to avoid both dangerous delay and needless panic. The first message tells us something happened. The later message tells us what it may mean. If you had to choose, which would worry you more, a large deep earthquake or a smaller shallow one near a city? Write your answer, because the difference between those two choices reveals why earthquake numbers alone never tell the full story. Now the map points to Japan, a country where earthquakes are not an unusual headline, but part of daily national planning. Japan lies where several tectonic plates meet, and its islands are surrounded by deep ocean trenches and active faults. The ground beneath Japan is not quiet, but Japanese scientists have built one of the world's most advanced systems for watching it. The usual expectation is that better instruments should make the future easier to predict. If thousands of sensors can detect tiny movements, perhaps they can warn us about the exact day and place of a major quake. That hope is powerful, but earthquakes do not provide a clean countdown. On July 28, 2026, the Japan Meteorological Agency listed a magnitude 7.1 earthquake in the Kumamoto region. The reported depth was about 10 kilometers, making it a shallow event near the southwest of Japan. The agency's detailed information allowed people and emergency teams to see the measured size, location, and shaking instead of relying only on rumors. What scientists expected was that such an event would be studied as a regional earthquake with possible aftershocks. What people feared was a signal that a much larger earthquake was about to strike somewhere else in Japan. Those are not the same claim. Japan's own warning system shows the difference. It can detect an earthquake after rupture begins and send alerts before the strongest waves arrive at locations farther away. That may provide seconds of warning, which can stop trains, open elevator doors, and give people time to protect their heads. But an early warning is not a prediction. It does not say, a quake will begin tomorrow at 3 in the afternoon. It says, a quake has already started, and strong shaking may reach you soon. That distinction matters more than it sounds. A few seconds cannot save every building or prevent every injury, but it can change what machines and people do in the moment. The system is useful because it reacts quickly, not because it sees the future. Japan also faces concern about the Nankai Trough. This is an underwater boundary where one plate is pushed beneath another south of the main Japanese islands. It has produced giant earthquakes in the past, sometimes in connected sections and sometimes in events separated by years. The expectation many people hear is that pressure is building, so a great quake must be scheduled soon. The reality is more difficult. Scientists can estimate long-term risk, but they cannot give a reliable exact date. A fault can remain locked for a long time, and the word overdue does not work like it does on a calendar. Japan has also used special advisories when a strong earthquake changes concern about a possible Nankai event. An advisory is not a promise that the larger quake will happen. It is a message to review preparation because the short-term risk may be higher than the background level. That is a subtle idea, but it protects people from two opposite mistakes. One mistake is ignoring a real hazard because nothing has happened recently. The other is believing that every advisory means disaster is certain. And now comes the reveal many viewers remember. A big earthquake can increase the chance of another earthquake in a nearby area, but the increase is not a magical signal spreading across the globe. Stress changes are strongest close to the rupture, and they weaken with distance. A study of global aftershock zones found that only a small share of major earthquakes caused a significant local increase in earthquake rates outside their immediate aftershock area. The exact number is not a promise about any single event, but the message is clear. Global connection is much weaker than online maps make it appear. Did you once think that a large earthquake in Japan could directly trigger earthquakes in Colombia or Spain? Tell us what you believed before hearing this, and subscribe if you want the next mystery explained with the same careful line between possibility and proof. Spain may seem like the odd country in this group. It is not usually the first place people name when they talk about giant earthquakes, but Spain is not free from seismic risk. The southern part of the country sits near the boundary between the African and Eurasian plates, and faults run through areas including Andalusia and the Granada region. The expectation is often that a European country with modern cities must be geologically calm. The actual pattern is different. Spain has frequent small earthquakes, with occasional stronger events that can cause damage. A lower average risk is not the same as zero risk. The Spanish National Geographic Institute, known as IGN, publishes earthquake catalogs and recent event lists. Those lists can show small earthquakes around Granada, including events too weak for many people to feel. When the catalog is updated quickly, a viewer may see many entries appear in a short burst. But a longer catalog tells a calmer story. The region has always had earthquakes because the plates are still moving. The new dots are not proof that Spain has suddenly joined the Ring of Fire. They are evidence that instruments and agencies are recording the activity that occurs in its own local setting. A magnitude 3.6 event near Armilla in the Granada area was listed by the IGN in 2026. That number means the quake released far less energy than a magnitude 7 event, but shallow depth and distance from homes can still decide whether people notice it. For someone under a building, a small sudden shake can feel very large. This is a key lesson. Earthquake danger is not controlled by magnitude alone. It also depends on depth, distance, ground type, building design, time of day, and whether the quake causes landslides or other hazards. Soft ground can increase shaking in some places. Older masonry buildings may respond differently from modern reinforced structures. A quake under an empty mountain may make headlines but cause little harm, while a smaller quake beneath a crowded neighborhood may become a tragedy. The next time you see Spain beside Japan in a list, pause before comparing the numbers. The list may be comparing two different kinds of activity, measured by different networks, with different levels of public attention. A shared date does not create a shared cause. What do you think is more misleading? Seeing too many earthquake dots, or seeing only one huge dot and ignoring all the smaller warning signs? Comment with your choice, and if the answer surprised you, give the story a like so more people can learn how to read a seismic map. Now cross the Atlantic to the United States. The country has several major earthquake regions, and they do not all behave in the same way. California is famous for the San Andreas Fault, but Alaska, Hawaii, the Pacific Northwest, Nevada, Utah, the central United States, and the eastern states also experience earthquakes. The expectation is that the United States earthquake story is mostly California. The reality is much wider. The USGS map can show dozens of magnitude 2.5 or greater events in a single day across the country and nearby areas, many of them too small for most people to feel. A magnitude 2.5 event is close to the lower edge of what a person might notice under good conditions. A network can record it even if nobody reports shaking. That is why public maps often look busier than personal experience. In Hawaii, earthquakes can also be linked to volcanic processes. Moving magma, changes in pressure, and the collapse of underground rock can create swarms of small earthquakes. These events may be important for volcano monitoring, but they do not mean that every fault in North America is preparing to rupture. Alaska sits near another powerful plate boundary. The state experiences many earthquakes, including deep and offshore events, because the Pacific Plate and other blocks of crust interact there. Its map can look active on an ordinary day, not because a global crisis is taking shape, but because Alaska is one of Earth's most active seismic regions. In the Pacific Northwest, attention often turns to the Cascadia subduction zone. This offshore boundary stretches from northern California toward British Columbia, where one plate is being pushed beneath another. Researchers have identified evidence of past great earthquakes, including about 13 major events in the last 6,000 years. That average works out to roughly one event every 500 to 600 years, but an average is not a timer. It does not mean that an earthquake must happen when the average is reached. The risk is real, yet the date remains unknown. The USGS and regional agencies do not say that a recent quake in another country proves Cascadia will rupture next. They study the zone using history, seafloor evidence, GPS measurements, and earthquake records. Preparation is based on hazard, not on a dramatic connection between unrelated headlines. The same logic applies to California. A local sequence can raise short-term concern near a fault, but that does not create a reliable forecast for the whole state. Scientists can describe probabilities and likely effects, while emergency planners focus on what people can do before the shaking begins. Here is a detail that seems small, but changes everything. The USGS says a temporary rise or fall in the worldwide number of earthquakes is part of normal variation. Neither a worldwide increase nor a worldwide decrease is a dependable sign that a large earthquake is about to happen. In other words, the planet can produce a busy-looking week without sending a hidden warning. Random chance can create clusters, just as tossing coins can produce several heads in a row. A cluster feels meaningful because the human brain is designed to search for patterns, even when the pattern is accidental. Do you think a worldwide earthquake map would look less frightening if it showed only earthquakes people could feel? Answer that in the comments, and stay with the evidence by subscribing for stories that do not turn normal Earth processes into fake predictions. To understand why the current moment feels unusual, we have to examine how news travels. Before smartphones, a small earthquake in another country might never reach your home. Today, an alert can arrive seconds after the event, followed by a map, a video, a post, a headline, and thousands of reactions. One earthquake becomes many appearances on your screen. The same event may be described by a local agency, the USGS, an international network, and several news outlets. To a viewer, that can look like several earthquakes, even though it is one earthquake repeated through different channels. Social media also rewards surprise. A post saying, "normal small quake recorded in a fault zone," spreads slowly. A post saying, "earthquakes everywhere, is something huge coming," spreads much faster, even when the second message has no scientific support. That does not mean every alarming post is dishonest. People may be frightened, and they may honestly describe what they see. But emotion is not a measuring instrument, and a crowded feed is not the same as a changing planet. Detection itself has improved. Seismometers are more sensitive, communication is faster, and computer systems can find smaller events in noisy data. In some places, local networks add hundreds of instruments that did not exist decades ago. If you compare the raw number of recorded earthquakes today with records from a century ago, you are not comparing equal systems. Older records missed many small earthquakes, especially in remote regions and poorer countries. A rise in recorded events can mean better listening rather than more shaking. There is another trap called catalog completeness. After a large earthquake, the ground may shake so much that smaller nearby quakes are hidden inside the noise. For a while, the network may actually detect fewer small events, even though many are happening. Later, when the signals are separated and reviewed, those events may be added to the catalog. The graph can then show a sudden burst of activity that partly reflects delayed detection. The data is valuable, but it must be read with knowledge of how the data was collected. Scientists also separate main shocks, aftershocks, foreshocks, and unrelated background earthquakes. A foreshock is a smaller event that is later recognized as a foreshock only after a larger earthquake happens. Before the larger event, nobody can know with certainty that the smaller quake had that role. This is why earthquake prediction is so hard. Many small earthquakes happen without a large earthquake following them. Many large earthquakes happen without a clear warning sequence that humans can recognize in advance. The expected pattern is tempting. Small shakes first, huge shake next. The actual pattern is messy. Sometimes small quakes are followed by a larger one. Usually they are not. and even experts cannot reliably label the future. That uncertainty is not failure. It is an honest limit of current science. If the world were truly entering a single global earthquake event, we would need evidence beyond a list of headlines. We would need a measurable physical process linking distant faults, a pattern stronger than normal chance, and independent confirmation from many monitoring agencies. So far, a busy map alone does not provide that evidence. Now let us compare the 5 places directly. Colombia has active subduction and mountain faults. Indonesia has many plate boundaries and island arcs. Japan sits at several dangerous boundaries and has an advanced warning network. Spain has active faults near the Africa-Eurasia boundary. The United States contains multiple separate seismic regions, from Alaska and Hawaii to California and Cascadia. These places share one planet, but they do not share one fault. The first expected story says the same mysterious force is pushing every location at once. The observed story says each region has its own local history, plate geometry, and normal range of earthquakes. The gap matters because a global explanation can hide the real local risks that emergency agencies need people to understand. For Colombia, that may mean learning how to respond to strong shaking and landslides. For Indonesia, it may mean knowing coastal evacuation routes after an offshore quake. For Japan, it may mean securing furniture, using alerts correctly, and understanding tsunami instructions. For Spain, it may mean checking older buildings and learning that moderate earthquakes are possible. For the United States, it may mean preparing differently in California, Alaska, Hawaii, the Pacific Northwest, or the Central States. The useful action changes by location, even when the fear begins with the same global map. And this situation is still happening right now in the only sense that truly matters. Earth's plates are moving at this moment, faults are storing stress, sensors are recording small vibrations, and agencies are updating their catalogs. There is no final day when the planet becomes safe from earthquakes, but ongoing does not mean escalating. A background process can continue, without moving toward a guaranteed disaster. The ocean keeps making waves every day, yet every wave is not the beginning of a tsunami. The same distinction helps with earthquakes. Continuous seismic activity is normal for a living planet. A temporary cluster can be important locally, but it is not automatically a step toward a global rupture. Still, we should not swing too far toward comfort. The fact that there is no proven worldwide increase does not make any single earthquake harmless. A normal event can still destroy a weak building, cut power, block roads, or send a tsunami toward a coast. The safest message is not "nothing is happening." The safest message is different things are happening, and we need to identify each one correctly. That is less dramatic than a doomsday prediction, but it is far more useful. Before the final piece, consider a thought experiment. Imagine that every earthquake on Earth stopped appearing on the internet for 1 week. The plates would still move, faults would still adjust, and instruments would still record signals, but your sense of danger would probably fall. Now imagine the opposite. Every tiny tremor, every aftershock, and every distant event appears as a red alert on your phone. The planet has not changed, but your experience of the planet has. This is the hidden force behind the phrase "earthquakes everywhere." It describes a real flood of information built from real events, but it can create a false impression of one connected emergency. The mystery is not that Earth shakes. The mystery is how quickly our minds turn scattered facts into one story. The biggest reveal is also the simplest. There is no accepted scientific evidence that earthquakes in Colombia, Indonesia, Japan, Spain, and the United States are currently part of one planet-wide chain reaction. Their activity can overlap in time because Earth has many active faults and because random clusters happen. Experts can study whether one earthquake slightly changes stress on another fault, especially nearby. They cannot turn that complex process into a reliable worldwide countdown. Anyone who claims to know the exact date of the next major earthquake is making a claim beyond what current science can support. That does not make science weak. It makes science careful. Science can tell us where hazards exist, how shaking travels, how buildings fail, how warnings work, and how to lower the chance of injury. It can also tell us what a recent quake does not prove. It does not prove that every distant fault is waking up. It does not prove that a megaquake is scheduled next. It does not prove that the number of earthquakes worldwide has suddenly changed. What it does prove is more grounded. A magnitude 7.4 event in Colombia deserves serious response. Earthquake sequences in Indonesia deserve careful tsunami and local hazard checks. A magnitude 7.1 earthquake in Japan deserves monitoring and preparation, especially in a country with major subduction risks. Small earthquakes in Spain still teach us that risk exists outside the most famous earthquake zones. The many events on United States maps remind us that the country has more than one seismic story. The planet is not sending one message. It is giving different regions different warnings about their own ground. And this is where the subject becomes personal. You may never feel a magnitude 7 earthquake. You may never live near a subduction zone, and you may never receive an emergency alert. But you still live on a moving planet, inside buildings that humans designed and maintained. The most important question is not whether the map looks scary today. It is whether your home, school, workplace, or family knows what to do when the shaking starts. During an earthquake, the basic advice is simple: drop, cover, and hold on. Drop low so the shaking cannot knock you down. Cover your head and neck under a sturdy table if one is close, or protect yourself beside an interior wall away from windows. Hold on until the shaking stops, because the thing protecting you may move. If you are near a coast and the earthquake is long or strong, do not wait for a perfect message before moving away from the shore. A tsunami can arrive after an offshore quake, and the first wave may not be the largest. Follow local warnings, move to higher ground or inland, and never go back just because the water looks calm. Preparation turns a mystery into a plan. Secure heavy shelves, keep shoes and a light near your bed, store water, learn how to shut off utilities if needed, and know how your family will contact one another. These actions do not predict earthquakes. They reduce the damage when prediction is impossible. So, are earthquakes happening everywhere? In one sense, yes. Earth is always shaking somewhere, and modern instruments now let us see much more of it. In the frightening sense of one hidden force striking Colombia, Indonesia, Japan, Spain, and the United States together, the evidence does not support that story. The real event is a meeting between deep geology and instant communication. The plates move slowly, but the information moves at the speed of light. That combination makes normal seismic life feel like a sudden worldwide alarm. The next time a map fills with dots, ask 3 questions. Are the events connected by one local sequence, or are they separated by thousands of miles? Are we seeing a true increase, or are we seeing better detection, more reporting, and random clustering? And what local action would actually protect people where the shaking occurred? If you can answer those questions, you are harder to frighten with a misleading headline. You can respect the danger without inventing a prophecy. You can look at a red dot on a screen and remember that behind it are real people, real buildings, and a real need for accurate information. Before you leave, make your answer part of the story. Subscribe if you want more science mysteries explained without exaggeration, turn on notifications so you do not miss the next investigation, and comment with this exact choice: global chain reaction or separate active fault zones. Then share this with someone who has been watching earthquake maps and wondering whether the planet is changing. A calm, accurate explanation can travel farther than a panic post, and sometimes that is the most useful warning we can give. Thank you for watching, and stay curious, stay prepared, and keep looking beneath the surface.